Hi everyone, this is our final presentation video for our final project of HLS course. So our project is speed up the training and inference process for multilayer perceptron. And this is our table of contents. So the goal of our project is use FPGA and HLS tool to build an accelerator that can speed up training and inference process of a multilayer perceptron of classifying handwritten digits. Although GPU dominates ML training, FPGA has its own advantages. For the first one, this consumes less power, and second, its latency is more predictable. Third, it's much cheaper, and fourth, the memory system can be specially designed to reduce requirement on memory bandwidth. The reason that we choose this specific model is that it is sophisticated enough for such simple tasks, and its propagation updates can be manually derived. And finally, it has great potential for more complex tasks, such as natural language processing and computer vision.
In terms of the specific model, we have a data set. Each image has 20 by 20 pixels, and the training set contains 4,000 samples, and the cross-validation set contains 100. There are 3 layers: one input layer, one hidden layer, and one output layer. The activation function we choose is sigmoid, and the loss function is the sigmoid cross entropy with regularization. This model heavily depends on matrix multiplication, which is why we put a heavy emphasis on it later on.
Here's the optimization techniques that we use in this project. Since we're using a small FPGA and the hardware resources are very limited, so we need to apply optimization strategically. The FPGA has limited computing and routing resources like DSP for multiplication. So we use some techniques like reusing the single core via tiling to save resources. And we also use different approaches to optimize our core to minimize the dependencies and pipeline the loops in the core for better performance. The board has also small on-chip storage, which is the BRAM. We try some techniques like training with small batches and use some shorter data types to save memory. Lastly, the board has very limited off-chip bandwidth. And data flow programmer is one technique that can possibly increase the throughput, but we did not use it for some reason. We will mention it in later slides.
Here's a table of all the results that we've for the core that we've implemented. We will come back to this shortly. But to establish a baseline, we had a vanilla approach with no hardware optimization. Our single core multiplies 2 square matrices, each with dimension of 10. And this gives us a latency of roughly 12,000 cycles. So the first optimization approach we tried is to pipeline the K loop. This gives us a latency improvement from 12K to 8K. With minimal hardware increase. The most increase was the LUTs, and we suspect that this was because of the control logic for a pipeline. The issue with this is that the II could only achieve 8 because there was a carry dependency. To test whether this is feasible or not, we wanted to try out 2 more optimizations under this constraint. The first one being swapping the KNM loop while still pipelining the K loop. This essentially allows us to compute a vector by vector multiplication, but for every single column. The latency improvement we saw was a 10 times improvement from 8,000 to 800 with some hardware increase. The memory partitions required for this was to split B by dimension 2 and split C matrix by dimension 2. Obviously, this doesn't solve the core issue of a carry dependency, but it does bring improvement. The other extreme approach was to pipeline the most outer M loop. We saw the latency improved from 12,000 to 67. While the II was achieved 1, the hardware explodes. We overexceeded the DSP available on the board, which is completely unfeasible. Which led us to the Scalar-Vector approach. This approach, without any hardware optimization, is the same as the vanilla approach, but with this, if we pipeline K, we are able to trade off a small resource increase to achieve a II of 1. And since there is no dependency, we see a 10 times improvement from roughly 12,000 cycles to roughly 1,000 cycles. Taking this a step further, we reordered the loop order and pipelined the end loop, essentially operating, applying the scalar vector optimization, but for all the M loops of matrix A. The memory partitions required for this is split A by dimension 2 and split C by dimension 2, as well as partitioning the temporary matrix used for computing the partial sum. This gives us a II of 1, and we see another improvement 10 times in latency at the expense of some increased hardware utilization. Lastly, we tried out the systolic array. Essentially, this allows each output cell to continuous compute at the same time. The hardware optimization was to pipeline K, unroll M and N. This obviously brings back the carry dependency, which gives us a II of 5 and uses a bit more hardware since we are computing all of the output cells at the same time. But the result latency is actually the fastest out of all implementations at 59 cycles. And so to summarize this table, we had the vanilla approach, but had carry dependency issues, which led us to the Scalar-Vector approach. Once the dependency was solved, we see it 10 times with every iteration. The systolic approach gave us the best results at 59 latencies, despite having the carry dependency issue back.
So let's talk about limited on-chip storage here. The FPGA that we use cannot train 400 images or 4,000 images at once because of limited VRAM. So we choose to separate the training into small batches, and we choose to train 100 images per batch so that the FPGA is able to store the images. We also use a smaller data type, which is half precision floating point instead of using single precision floating point, so that the memory usage is halved. And the shorter data type also reduces the cycles needed for computations like multiplication from 4 cycles to 3 cycles. Using smaller data type has very little impact on the final accuracy. And the communication overhead is a big portion of our performance. As I just mentioned, our data type is huge. The total transaction needed is around 60 megabytes. It results a large communication overhead. One solution for that is the data flow programmer can enable task level pipeline. It allows the function to start operation before previous function completes all the operations, which can potentially decrease the communication overhead. But this programmer needs to duplicate arrays to minimize dependency. And since our memory usage resource is limited, therefore we did not use it.
For the result, we can see that we have achieved a 10 times speed up in the reported latency and a 16.7 speed up in execution time on that board. To be noted, this excludes the communication overhead, and the optimization approach used no excessive resource usage. And one thing is that the cost function with sigmoid still consumes 30% of the DSP, which can be further reduced by changing the cost function by a ReLU function. And in conclusion, that we are using tiling and a single core to make our implementation more flexible in application. And we explore several matrix multiplication structures of all of the approaches. The systolic array was the best. We also used small batch training applied in FPGA to fit all the constraints in hardware. We also accelerated, in final words, we also accelerated the training and inference of the 3-layer MPL model by 16.7 times. Thank you.